Section 8.6 is called Representing Functions as Power Series. So the first thing we want to do is just recall a little bit of the information we've already talked about. Remember back in Section 8.2 we introduced the geometric series. So geometric series we learned to have the form summation from 1 to infinity of some constant out front times some common ratio being raised to the n minus 1 power. We know that this converged when the absolute value of the common ratio was less than 1 and that it converged to a over 1 minus r. If the absolute value of r was greater than or equal to 1, it diverged. If we consider the geometric series, general form, remember that we talked about we can change the starting place of a summation without changing the series by accounting for that power on the inside. So if I wanted to write this as the same series but starting with an n of 0, if I've subtracted 1 from the outside piece, the summation, then to account for that, remember we added 1 to the power inside of the series. So instead of n minus 1, it has been accounted for by adding 1 and leaving you with the power of n. These two things are equivalent. So this is just another way of writing a geometric series. This is important because if you recall from Section 8.5, the form of a power series is a sum from 0 to infinity of some coefficient times your variable x to the nth power. So what we're going to do in this section is we're going to try to take functions that were given and write them as a power series. So the idea is I'm going to take that function, I'm going to try to represent it in the form of a over 1 minus r to write it as a geometric series, which is in fact a power series. This section is almost working backwards from what we've previously done with geometric series. Here's our first example. I want to represent the function as a power series. So I'm given the function 2 divided by 1 minus x. Now, first thing I'm going to do is try to turn this into a geometric series, meaning I want what I'm looking at to have the form a over 1 minus r. Now, we're pretty close to that form here, right? So the 2 that you see up top would be my a. I have a 1 minus. What's being subtracted from 1 is our r. So our r is x. I know that this given function, 2 over 1 minus x, because it has this form, can be written as a geometric series from 0 to infinity, meaning this form, a times r to the n. We want to be sure that we plug in what are our a and our r. So what I'm looking at is the sum going from 0 to infinity. Our a was 2. And our r was just x being raised to the nth power. I've taken the function and I have written it as a geometric series, also a power series. When is this true? Well, remember I stated it up at the top again to remind us. I know that this series converges to this form when the absolute value of r is less than 1. So I can write this function as this series when the absolute value of r is less than 1. Notice that our r was x, so when the absolute value of x is less than 1, meaning when negative 1 is less than x is less than 1. If I wanted to talk about these endpoints to see are they included in the values that allow me to transform this function, remember we would say we would have to check the endpoints. However, a nice fact is that for geometric series, you will never include the endpoints. Geometric series, the interval of convergence will always be strict. That's a nice fact to know that can save you a little bit of time. So I'll go ahead and write it. So for geometric, always strict. Meaning the interval of convergence, or the interval for which this relationship is good, is negative 1 up to 1. So this is your power series, and it's for that interval negative 1 to 1. I am going to come over to the side and show you that in fact it's true. We don't include those endpoints. So notice when x is equal to negative 1, that our series would be the series going from 0 to infinity of 2, I'm checking negative 1, times negative 1 to the n. So I'm looking at a series. It is an alternating series, so you could check your alternating series test. Obviously, the limit of the inside for part 2 doesn't equal 0. So maybe that's a tip that we should look at the limit of the inside sequence. As a whole. The limit of this does not equal 0. So by the test for divergence, this diverges. If we check what happens when x equals positive 1, this would be the series going from 0 to infinity of 2 times 1 to the n. So you're looking at the series 0 to infinity of 2. Again, the limit of the sequence inside is 2, which does not equal 0. So test for divergence says that this also diverges, which means I don't want to include either endpoint. So you can check them with the methods we used, or you could just know the fact that for geometric series, this is always strict inequality. Right? We do not include the endpoints. I've got another example of this. So part B. I want to represent the function 1 over 1 minus 3x as a power series. So again, what I'm trying to do is first write it as a geometric series because it mimics the form a over 1 minus r. I see a relationship here. Well, my numerator is the a. I do have the 1 minus, and what's being subtracted from 1 is my r. So I can take this function and I can write it as the geometric series from 0 to infinity, a r to the n. Plugging in our a, I have series going from 0 to infinity of 1. Our r is 3x, and it's being raised to the nth power. It's a good habit to get into to separate the x's to a power. Later we're going to talk about taking derivatives and antiderivatives of power series. So it's just a good habit to go ahead and separate the powers of x. So I'm going to rewrite this from 0 to infinity of 3 to the n times x to the n. Right, the forms are equivalent. Now, when is this good? I need to know, when does this relationship hold? Well, it holds when the absolute value of r is less than 1, meaning the absolute value of 3x is less than 1. So negative 1 is less than 3x is less than 1. Dividing every piece by 3, negative 1/3 is less than x is less than 1/3. Again, it's a geometric series, so it's going to be strict, meaning our interval is negative 1/3 up to 1/3, endpoints not included. Part C. Now I have the function 1 over 8 minus x. And I'm thinking about that geometric series form that I want. I want this as a over 1 minus r. If you're looking at this, there's an issue. In that denominator, I have an 8 minus, not a 1 minus. So the first thing I want to do is find a way to transform 8 into 1. Well, if I divide 8 by 8, that would give me what I want, but if I do it to one piece, I have to do it to every single piece. Again, I wouldn't necessarily write this each time, but it's the equivalent of multiplying the numerator by 1/8 and multiplying the denominator by 1/8. What have I multiplied the expression by? 1, so I haven't changed the value. So this is the same as 1/8 divided by 8 over 8 minus x over 8. So I have 1/8 divided by 1 minus x over 8. Now I have my 1 minus. What's being subtracted from that is our r. What's in my numerator is my a. I know that this can be written as a sum going from 0 up to infinity of a r to the n. So what I have is sum from 0 to infinity. Our a is 1/8. Our r is x over 8, and it's being raised to the nth power. Again, I like to separate the powers of n from the rest of it. So I'm just going to rewrite this summation as 0 to infinity. Here I already have a 1/8 times. This is a 1/8 being raised to the n times an x to the n. Neat way of writing this, you have 0 to infinity of, in my numerator, x to the n. Here I have 1/8 raised to the n plus 1, or a denominator of 8 to the n plus 1. I need to know when is this expression good for, so I need to find the interval that this holds. This holds when the absolute value of r is less than 1. Our r, where did it go, is x over 8. So negative 1 less than x over 8 less than 1. Multiplying every single piece by 8, I have negative 8 less than x less than 8. Again, it's a geometric series, so it's going to be strict. So this is good for the interval negative 8 up to 8. Example 2. Find the first 4 terms of the power series expansion 4. 3 divided by 1 plus 2x. So this time they're not asking me necessarily for the summation itself, but for the expansion, the first 4 terms. I would still try to relate this to my geometric series form, the a over 1 minus r, right? What the geometric series converges to. Now, in my denominator, I do have the 1 that I want, but notice it's a plus, not a minus. So I want to manipulate this to look like 1 minus. I leave my numerator alone. This is the same as 1 minus a negative 2x. So the idea is instead of plus, I write it as minus a negative. I now have something being subtracted from 1, which is my r. What's in my numerator is my a. So I'm going to write this as the series going from 0 to infinity of a r to the n. So series going from 0 to infinity, our a was 3. Our r is negative 2x to the nth power. What I'm looking at is a summation from 0 to infinity of 3 times negative 2 to the n, x to the n. They want the first 4 terms, so I'm going to expand this summation. So when n is equal to 0, notice I would have 3 times negative 2 to the 0, x to the 0. I'll come back and clean it up. Plus, when n is equal to 1, I would have 3 times negative 2 to the first power times x to the first power. When n is equal to 2, I would have 3 times negative 2 squared, x squared. And when n is equal to 3, I would have 3 times negative 2 cubed, x cubed. That would give me the first 4 terms. So what I'm looking at is 3 times 1 times 1, so just 3. Here I have 3 times negative 2, giving me a negative 6x. Here I have 3 times negative 2 squared, so 3 times 4, giving me 12x squared. And for my last term, I have a negative 2 cubed, which is negative 8 times 3, giving me a negative 24x cubed. So final answer, I have 3 minus 6x plus 12x squared minus 24x cubed. We we could talk about on what interval this summation or this transformation is good for in the same way we did back in example 1. Part B. Now my function is 2 divided by 1 plus x squared. I'm wanting to take this and write it as a power series. I want to expand it for the first 4 terms. I'm already thinking about that form, a over 1 minus r. Again, in my denominator, I already have the 1 that I need, but this is a plus, so I want to rewrite that plus as a minus. So I have 1, the plus can be written as minus a negative x squared. The part that I'm subtracting from the 1 is my r. The numerator is my a. I know this can be written in the form from 0 up to infinity of a times r to the n. Our a is 2, our r is negative x squared being raised to the nth power. So what I have is my sum from 0 up to infinity of 2 times negative 1 to the n times x squared to the n. Rules of exponents say a power to a power, you multiply. So I'm looking at the sum going from 0 to infinity of 2 times negative 1 to the n, x to the 2n. They only want the first 4 terms of this, so we want to expand it, starting with an n of 0. When n is 0, I would have 2 times negative 1 to the 0, x to the 2 times 0. When n is 1, I would have 2 times negative 1 to the 1, x to the 2 times 1. When n is 2, I would have 2 times negative 1 squared, x to the 2 times 2. When n is 3, I would have 2 times negative 1 cubed, x to the 2, let me rewrite that, x to the 2 times 3. So what I have is 2 times 1 times 1. Here I have 2 times negative 1 times x squared, so negative 2x squared. Here I have 2 times negative 1 squared, so just a positive 2 times x to the 4th. Here I have 2 times negative 1 cubed, giving me a negative 2, x to the 2 times 3 is 6. I have the first 4 terms that they were looking for. So 2 minus 2x squared plus 2x to the 4th minus 2x to the 6th. Again, you could talk about the interval for which this relationship holds in the same manner we did back on the example 1, part A, B, and C. The question that's going to arise in the rest of this section, which you'll talk about in class, is what happens when I have a function that doesn't have the form a over 1 minus r, and I can't manipulate it to that form? How can I take those types of functions and write them as a power series? One of the ideas you're going to use is maybe I can't use the function itself to write it as an a over 1 minus r, but what if the derivative of this function has this form? Or what if the antiderivative of this function has this form? I would take whatever I can manipulate into this form, and then I can integrate the power series or take the derivative of the power series to get the function I was asked about.